Imagine this traveller drawn here by something you can't quite name, a quiet pull, as if the cosmos itself opened a small doorway for you tonight. Out there an object drifts between Mars and the Sun, a fragment of another star, silent and impossibly precise. What are the odds that its path, a 1 in 20,000 trajectory, brushes so close to a world where life may once have risen? What if its timing isn't coincidence at all? What if the universe is whispering through this visitor? A message folded into carbon ice, a question shaped in starlight waiting for someone like you to notice. Stay a while, traveller. Let's drift through the silence together. In the quiet expanse of our solar system, where dust radiation and the faint echoes of stellar history flow continuously through space, the arrival of an interstellar object is never a trivial event. Such encounters are rare in the chronology of planetary science, and rarer still are those that intersect so elegantly with ongoing questions about life beyond Earth. The object designated 3I Atlas represents only the third confirmed visitor from another star system, and yet its timing, trajectory and chemical properties have placed it at the centre of an unusually reflective moment in modern astronomy. 3I Atlas carries within its nucleus a high concentration of carbon dioxide, enough according to spectral analysis to contribute meaningfully to a planetary atmosphere if released in significant quantities. This observation becomes particularly striking as the object heads toward Mars, a planet whose thin CO2-dominated atmosphere is at the core of ongoing research into climate history and past habitability. For planetary scientists, such a coincidence invites thoughtful scrutiny. For the broader scientific community, it offers an opportunity to reconsider the interconnections between organic chemistry, orbital mechanics, and the evolution of planetary environments. Its trajectory is equally compelling. Calculations place 3I Atlas on a path that will bring it within approximately 30 million kilometers of Mars, a proximity notable not for its danger, but for its precision. This passage occurs during a period when the object will be obscured from Earth-based observation by the Sun's glare, creating a natural window of limited visibility at the very moment of closest approach. From a scientific standpoint, this alignment is perfectly compatible with the mechanics of hyperbolic motion. Yet its correlation with the latest Martian discoveries invites a broader contemplation of timing in cosmic events. Just months before 3I Atlas was identified, NASA's Perseverance rover uncovered potential biosignatures in sedimentary samples from Jezero crater. These leopard spot mineral textures containing compounds associated with biological processes on Earth represent some of the strongest hints yet that Mars may once have supported microbial life. They do not confirm the existence of ancient Martian organisms, but they strengthen the case for a once habitable world. Thus, two narratives converged in the same time frame: the search for past life on Mars and the unexpected arrival of an object with the chemical capacity to alter a planetary atmosphere. The scientific method cautions against reading intention into coincidence. Interstellar objects follow trajectories shaped by gravitational encounters across millions of years, long before human instruments were capable of detecting them. Yet science also encourages the recognition of meaningful questions, those worth exploring, not because they imply purpose, but because they refine our understanding of natural processes. From a chemical perspective, 3I Atlas offers a rare sample of material formed in an environment beyond our solar system. Its elevated CO2-H2O ratio suggests formation near the carbon dioxide ice line of its home star, a region where water remained gaseous while CO2 froze into solid layers. This composition provides researchers with new constraints on models of disk chemistry, star formation, and the distribution of volatiles across planetary systems. Each measurement of its spectral emissions becomes a data point in a larger effort to map the diversity of interstellar chemistry. From an orbital perspective, its hyperbolic path reinforces the idea that such visitors may be more common than once assumed. Improvements in survey telescopes, automated detection systems, and deep sky imaging pipelines mean that future interstellar objects will likely be identified earlier and with greater precision. 3I Atlas therefore serves as both a scientific subject and a benchmark, an opportunity to refine detection strategies and interplanetary observation protocols. Yet perhaps the most important element of this encounter is not the object itself, but the scientific context into which it arrives. Mars is undergoing a renewed phase of examination, its climate history, atmospheric loss mechanisms, and sedimentary record all point toward a planet that was once far more Earth-like. The search for life there requires a multidisciplinary understanding of geology, atmospheric chemistry, and planetary evolution, exactly the fields enriched by studying interstellar objects. In this sense, 3i Atlas becomes part of a larger scientific dialogue. Not a cause, not a catalyst, but a reminder of the interconnectedness of cosmic phenomena. It illustrates that planetary science does not occur in isolation. It is shaped by events near and far, by local processes, and interstellar visitors, by the quiet persistence of rovers on Martian soil and the long trajectories of objects formed around distant suns. The arrival of 3i Atlas does not imply intention, but it does encourage reflection. It underscores the need to maintain scientific curiosity rather than certainty, to allow the unknown to coexist with evidence, and to recognise that the universe often presents phenomena whose significance emerges only over time. In the coming months, as the object approaches perihelion and begins its outward journey back toward interstellar space, researchers will continue to gather data. Some of it will be consistent with existing models. Some of it will challenge assumptions. All of it will contribute to a more complete understanding of how planets form, how atmospheres evolve, and how life might arise or fail to arise across the galaxy. 3i Atlas is not a message nor a threat, nor a cosmic anomaly demanding interpretation. It is a natural traveller from another star system rich in carbon dioxide drifting through our solar neighbourhood at the exact moment humanity is reconsidering the conditions required for life. Its presence is scientifically meaningful not because of what it intends, but because of what it reveals about the chemical and dynamical diversity of the universe. And in that quiet alignment between motion and inquiry, between discovery and coincidence, astronomy finds its deepest purpose not to impose meaning on the cosmos, but to understand the mechanisms by which the cosmos creates meaning of its own. The search for life beyond Earth has always unfolded, slowly driven not by dramatic discoveries, but by the accumulation of subtle clues. In recent years, Mars has become the focal point of this search, and among its many regions, Jezero Crater has emerged as one of the most promising windows into the planet's ancient environment. The Perseverance rover operating there since early 2023 has spent more than 4 years conducting a geological and geochemical survey of an area once shaped by flowing water. What it has uncovered does not yet confirm life, but it offers compelling evidence that Mars once hosted environmental conditions capable of supporting it. One of the rover's most significant findings involves the so-called leopard spot textures detected within samples collected at the Shavia Falls region of the ancient delta. These patterns might appear unremarkable at first glance, but to planetary geologists they represent a form of textural and mineralogical organisation that often arises from interactions between water sediment and chemical gradients. On Earth, similar features frequently emerge in environments shaped by microbial activity. Minerals such as vivianite and greygite, both detected in these Martian samples, are particularly noteworthy. Although they can form through non-biological pathways, they are also associated with metabolic processes in Earth's aquatic ecosystems. The discovery does not claim that life existed on Mars. Instead, it highlights the possibility that geological and chemical conditions favourable to life once existed in Jezero Crater, roughly 3.5 billion years ago. This period coincides with a chapter of Martian history during which the planet had a thicker atmosphere, more stable liquid water, and potentially habitable lakes and rivers. The deltaic environment preserved within Jezero provides an especially strong context for biosignature preservation. River sediments can trap organic molecules, maintain stratified chemical conditions, and preserve structures that record environmental changes with remarkable fidelity. Another layer of importance emerges from the rover's continuous high-resolution study of the Martian sedimentary record. Instruments on board Perseverance, including X-ray spectrometers, Raman spectrometers, and multispectral imagers, allow scientists to reconstruct the mineralogical history of rocks with unprecedented precision. These observations reveal that the crater's mudstones formed in stable, long-lived aqueous environments. Persistent water is one of the most important preconditions for habitability, and its presence strengthens the argument that Jezero may once have been home to microbial life, or at least prebiotic chemical systems. The rover's discoveries also intersect with a broader scientific context. The recent detection of 3I Atlas, only the third confirmed interstellar object to pass through our solar system, has coincided with the period during which these Martian biosignature candidates were identified. Although the two events are not causally related, their alignment underscores how planetary science increasingly operates within a multi-scale framework. Questions about the origins of life now extend beyond individual planets to encompass interstellar chemistry, planetary system evolution, and the distribution of volatile compounds across the galaxy. Mars represents the local chapter of this broader inquiry. The planet's ancient hydrology, current atmospheric composition, and sedimentary geology all point toward a world that underwent significant climatic change. Understanding whether life existed there requires integrating data from surface exploration laboratory experiments and orbital spectroscopy. Perseverance's samples, once returned to Earth through a future Mars sample return campaign, will be studied with instruments far more sensitive than those available on the rover, enabling analyses of organic molecules, isotopic ratios and microstructures that could reveal evidence inaccessible through remote sensing alone. Despite the enthusiasm surrounding these findings, scientific caution remains essential. Many geological processes can mimic biological signatures, especially in environments dominated by iron and sulfur-rich minerals. The challenge is to differentiate patterns formed by abiotic chemistry from those shaped by biological metabolism. This distinction demands careful statistical modelling, experimental replication, and comparisons across terrestrial analogue environments. As such, the current results should be interpreted as biosignature candidates, not confirmations. What makes the Perseverance mission scientifically compelling is not simply the possibility of life, but the methodological rigour with which that possibility is being explored. Every drilled core, every mineralogical analysis, and every spectroscopic measurement contributes to a cumulative dataset that refines our understanding of early Mars. The rover's work demonstrates the power of persistent systematic exploration. It also underscores an important truth: evidence of life, if it exists, will likely appear not as a dramatic revelation, but as a gradual convergence of chemical, geological, and environmental patterns. In this sense, the mission reflects the broader philosophy of astrobiology, that the search for life is fundamentally a search for context. Before life can be identified, the conditions that support it must be characterized. Before claims can be made, the uncertainties must be addressed. Mars offers a unique opportunity to study a world where habitability may have arisen independently from Earth. Whether or not life ever emerged there, understanding why it did or did not has profound implications for the distribution of life in the universe. As Perseverance continues its work, Mars invites us to consider a simple, enduring scientific question. If life can emerge once under the right conditions, how often might those conditions occur elsewhere? The answer will come not from speculation but from data. One mineral grain at a time, one sediment layer at a time, one quiet discovery at a time. The discovery of 3 Atlas on July 1, 2025 marked a pivotal moment in the study of interstellar objects. Detected by the Asteroid Terrestrial Impact Last Alert System ATLAS, the object immediately distinguished itself from typical near-Earth asteroids through its velocity trajectory and orbital eccentricity. The parameters calculated during the first days of observation revealed an unmistakable signature of interstellar origin, a hyperbolic orbit with eccentricity greater than 1. This mathematical property alone confirms that 3I Atlas is unbound to the Sun. It did not originate within our planetary system, and will not remain within it. Interstellar objects provide rare opportunities to examine material formed in environments fundamentally different from our own. Prior to Atlas, only 2 such visitors were confirmed, 1E Oumuamua in 2017 and 2E Borisov in 2019. Each contributed valuable data to planetary science, but also raised questions about the diversity and frequency of material ejected from other star systems. With 3I Atlas, researchers now have a third data point, still far too few for robust statistical models, but sufficient to begin identifying patterns and outliers. Initial spectroscopic observations of 3I Atlas were conducted using both the James Webb Space Telescope JWST and the Spherex infrared mission, allowing scientists to characterize the composition of the outcast material released as the object began to warm under solar radiation. One of the most striking findings was the dominance of carbon dioxide in the coma, with a CO2 to H2O ratio estimated at approximately 8:1. This value is unusually high compared to solar system comets, which typically exhibit water as the primary volatile component. By contrast, the chemical profile of Atlas suggests formation conditions near a region in its home system, where carbon dioxide ice was abundant and water remained less stable. The implications are significant. Such a high CO2 concentration hints at a protoplanetary disk chemistry, different from that of our own early solar nebula. It may also indicate prolonged exposure to cosmic radiation in interstellar space, which can alter the upper layers of cometary nuclei through the slow accumulation of carbon-rich products. These hypotheses remain under investigation, but together they demonstrate how interstellar objects can broaden our understanding of the chemical diversity present across the galaxy. Another notable observation emerged from ground-based telescopes, and amateur astronomers a faint green glow surrounding the object during early September. On Earth, this coloration is usually attributed to the presence of diatomic carbon, C2, or cyanide compounds, both of which emit green light when excited by ultraviolet radiation. Though not inherently exotic, the prominence of such emissions in 3I Atlas adds to the picture of a chemically unusual object. If confirmed, these compounds could offer additional clues about the photochemical environment in which the object formed. Scientific institutions have thus far characterized Atlas as a natural comet, and all available data support that conclusion. Its motion conforms to predictions based on solar gravitational influence. Its acceleration pattern matches known models of volatile outgassing, and no artificial signatures such as narrowband radio emissions or anomalous propulsion have been detected. Yet the object remains scientifically noteworthy, precisely because its chemistry does not easily fit within established comet categories. This complexity underscores why interstellar objects occupy such an important role in planetary science. They are not only travellers, but also sampling mechanisms and natural couriers, carrying material from environments we may never physically reach. In effect, 3I Atlas represents a fragment of another solar system's geological past, preserved over millions of years and delivered into ours by gravitational chance. The context surrounding its arrival further elevates its scientific interest. As Perseverance investigates the possibility of ancient Martian life, an object rich in carbon dioxide and organics is passing through the inner solar system. Although these events are unrelated in a causal sense, their concurrence illustrates how planetary science increasingly intersects with broader astrophysical processes. The conditions that allow life to emerge are influenced not only by local geology and climate, but also by the availability and distribution of volatile materials that may in part originate beyond the planetary system itself. Interstellar objects like Atlas therefore help address foundational scientific questions. How common are volatile-rich bodies in the galaxy? What chemical environments contribute to prebiotic chemistry? How do planetary systems exchange material over astronomical timescales? The answers will not emerge from a single observation, but from the gradual accumulation of data across multiple events. Atlas contributes to that process by expanding the known diversity of cometary compositions and by challenging existing assumptions about where and how key volatiles form. As the object continues toward perihelion, where solar heating will maximize outgassing, scientists anticipate additional compositional changes that may reveal deeper layers of its nucleus. Some volatiles may become detectable only at higher temperatures, others may diminish as surface deposits sublimate. Post-perihelion observations will therefore be critical in determining whether the 8:1 CO2 ratio reflects the object's bulk composition or merely its outermost layers. In this sense, 3I Atlas functions as both a scientific subject and a case study in observational limitations. Its trajectory, short observational window, and temporary solar obstruction challenge researchers to make careful use of limited data. Yet these challenges also reflect the reality of studying rare interstellar phenomena. The opportunity is brief. The uncertainties are large, and the insights when they emerge can reshape long-standing models. 3 Atlas does not provide answers to every question raised by early observations, but it advances the scientific conversation in meaningful ways. Its chemistry is unusual, its origin compelling, and its presence timely. Whether or not it resembles other interstellar objects that will be discovered in the future, it reinforces a central principle of planetary science. To understand the evolution of worlds, we must look not only inward to our solar system, but outward to the greater galactic environment. The upcoming passage of 3I Atlas near Mars represents a significant opportunity for planetary scientists, not because of any immediate physical interaction, but because of the unusual geometry and timing of the encounter. According to current orbital calculations, the object will sweep past Mars on October 3, 2025, at a distance of roughly 28-30 million kilometers. Though this separation is vast by human standards, nearly 75 times the distance from Earth to the Moon, it is remarkably close when viewed in the context of interstellar trajectories. For a hyperbolic visitor crossing the solar system at tens of kilometers per second, such proximity is far from guaranteed. The most compelling aspect of this encounter is not the distance, however, but the observational conditions under which it will occur. As 3I Atlas approaches Mars, the alignment of the Sun-Earth and the object will place Atlas in solar conjunction, rendering it effectively invisible to Earth-based telescopes for several critical weeks. In practical terms, this means that many of the object's most scientifically informative behaviours, changes in outgassing coma structure or spectral content, will occur precisely when our most powerful observational assets are unable to directly monitor it. This is a natural limitation of celestial mechanics rather than an anomaly. Solar conjunction regularly interrupts communication with Mars, spacecraft complicates deep space navigation, and obscures solar system objects that pass near the Sun from Earth perspective. Still, the timing is noteworthy. The weeks surrounding perihelion are typically when a comet's activity peaks, as solar heating drives the sublimation of volatile materials. For a chemically unusual interstellar object like 3I Atlas, this period could reveal deeper layers of its nucleus or shifts in the relative abundances of major volatiles data, essential for understanding its formation environment. Yet the Sun's glare will prevent continuous Earth-based monitoring during precisely this interval. Fortunately, Mars itself offers a partial solution. Multiple orbiters operated by the European Space Agency ESA and other international partners will attempt targeted observations during the flyby. Mars Express, with its capable imaging systems, and the Trace Gas Orbiter TGO equipped with advanced spectrometers, have the potential to record valuable data while Earthbound instruments remain effectively blind. Although these orbiters were not designed for interstellar object characterization, their instruments can detect spectral signatures, analyze gas emissions, and in optimal conditions, image the extended coma surrounding the object. The scientific goals of these observations are straightforward. Researchers aim to refine spectral measurements of volatile compounds, particularly carbon dioxide, carbon monoxide, water vapor, and any transient organic species. These measurements will help determine whether the unusually high CO2 abundance represents a surface phenomenon or a deeper structural property of the nucleus. Additionally, imaging may reveal the coma morphology, including possible jet density gradients or asymmetries driven by rotational dynamics. Any such observations would contribute to a more nuanced understanding of the physical behaviour of interstellar objects as they interact with solar radiation. The flyby's value extends beyond compositional studies. Precise tracking of 3I Atlas as it passes near Mars provides another opportunity to verify its non-gravitational acceleration profile, a key parameter in distinguishing natural cometary behaviour from more exotic interpretations. Objects like 1I Oumuamua displayed acceleration patterns that challenged conventional explanations, prompting discussions about solar radiation pressure, outgassing asymmetry, and controversially non-natural origin hypotheses. By contrast, early measurements of Atlas suggest that its slight deviations from pure gravitational motion correspond well with expected outgassing forces. Still, the Mars encounter offers an occasion to refine these measurements under different thermal conditions. In addition, the geometry of the flyby may allow scientists to examine how the object's coma interacts with the solar wind in a region of space where the magnetic and plasma environment differs from near-Earth space. Such data can inform models of how interstellar volatiles behave under varying heliophysical conditions, adding to our broader understanding of how material from other stellar systems evolves during its passage through ours. Despite these opportunities, it is important to maintain scientific perspective. Even if 3I Atlas were to release its entire mass of carbon dioxide into Mars's atmosphere, the contribution would be negligible compared to the planet's overall atmospheric loss rate. Mars's thin envelope is shaped by billions of years of solar wind stripping and the absence of a protective global magnetic field. No single object, no matter its composition, could meaningfully alter this trajectory. The significance of Atlas's chemistry lies not in its potential to modify a planet, but in what it reveals about the diversity of interstellar materials and the processes by which volatiles form, migrate and evolve. Ultimately, the October encounter underscores the delicate balance between opportunity and limitation inherent in planetary science. The flyby occurs at a moment that maximizes scientific intrigue, but not necessarily observational convenience. Yet this challenge reflects the reality of studying dynamic celestial phenomena. Researchers must work within the constraints imposed by orbital geometry, available spacecraft, and the physics of light itself. What the Mars flyby can offer is not answers to every question about 3I Atlas, but a clearer understanding of its physical behaviour during a period of heightened activity. Combined with post-conjunction observations later in the year, these data will contribute to a growing body of evidence about the nature of interstellar objects and the environments that produce them. As Atlas continues toward perihelion and then back into the outer solar system, the scientific community will synthesize data collected from multiple vantage points, Earth, space telescopes and Mars orbiters, to build a comprehensive picture of this rare visitor. In doing so, researchers take another step toward answering broader questions about the composition frequency and origins of objects that wander between the stars. As observational datasets on 3I Atlas accumulated through mid-2025, researchers began encountering a pattern familiar in the study of rare celestial phenomena, a growing set of measurements that fit established models, interspersed with results that resisted immediate classification. This is not unusual. Scientific understanding advances through the resolution of discrepancies in interstellar objects because of their scarcity naturally challenge existing assumptions. Yet the anomalies associated with 3I Atlas prove significant enough to prompt focused analysis across multiple research groups. One of the earliest puzzles involved the brightness variations reported in July and August. Photometric data revealed fluctuations that did not align cleanly with standard rotational models. Typically, as a comet spins, variations in its surface reflectivity or geometry produce predictable cycles in brightness. For Atlas, however, the observed fluctuations lacked a simple periodicity. Several explanations remain plausible: complex rotational states such as non-principal axis rotation, or tumbling heterogeneous surface composition, or asymmetric outgassing. These possibilities are well within the range of conventional comet behaviour. Nevertheless, the absence of a stable repeating light curve complicates efforts to determine the object's precise rotation rate, which in turn limits the ability to model the orientation of active regions on its surface. Another point of scientific interest concerns the outgassing profile. While spectroscopic measurements clearly show that carbon dioxide dominates Atlas's volatile emissions, the volume and consistency of these emissions introduced questions. The estimated gas production rate appeared higher than expected for an object at its heliocentric distance, especially during late July, when solar heating was still relatively modest. Elevated CO2 activity is unusual but not unprecedented. Several distant solar system comets exhibit CO2-driven activity at large distances due to the lower sublimation temperature of carbon dioxide ice. However, the combination of high CO2 abundance and sustained activity at significant heliocentric distances remains atypical enough to warrant continued monitoring. The coma morphology presented a third area of uncertainty. Telescopic imaging revealed subtle asymmetries in the distribution of dust and gas surrounding the nucleus. though data resolution was insufficient to determine their origin conclusively. Asymmetrical comae can emerge from uneven solar heating surface jets or complex nucleus geometries. They can also arise from observational artifacts connected to instrument sensitivity or atmospheric interference. Without higher resolution imaging such as that expected from the Mars, flyby definitive interpretation remains premature. A fourth category of anomalies relates to the object's non-gravitational acceleration. Many comets experience small deviations from purely gravitational trajectories due to outgassing forces. In Atlas's case, preliminary orbital solutions indicated slight but measurable accelerations that fit broadly within expected ranges. However, some datasets suggested deviations that did not align perfectly with early outgassing models. These inconsistencies did not imply unnatural behaviour. Instead, they highlighted the challenge of modelling acceleration in objects with unknown surface properties, uncertain rotation states and volatile compositions not yet fully characterised. As more observations were collected, orbital solutions gradually converged, reinforcing the likelihood that outgassing remains the dominant explanation. Finally, the statistical context surrounding 3I Atlas drew scientific attention. Interstellar objects were once thought to be exceedingly rare, but the detection of 3 such objects within less than a decade suggests that they may be far more common than originally estimated. This inference has led to ongoing revisions of interstellar population models. Atlas's relatively large estimated size, several kilometers in diameter, depending on albedo assumptions, raises additional questions. Is it an outlier in size distribution or representative of a broader population previously missed by detection systems? The answer carries implications for theories of how material is ejected from forming planetary systems, and how frequently such fragments traverse interstellar space. Across these anomalies, the scientific approach remains cautious, disciplined, and methodical. Anomalies do not imply extraordinary explanations. They indicate areas where current models lack sufficient granularity or where new data has yet to be reconciled with established theory. This process, identifying inconsistencies, refining hypotheses, and expanding models, is foundational to astrophysics. Objects like 3I Atlas serve as catalysts for scientific refinement, compelling researchers to revisit assumptions about cometary chemistry, interstellar transport processes, and the physical evolution of volatile rich bodies. What distinguishes Atlas is not the presence of anomalies, but the combination of unusual properties: a high CO2-H2O ratio, early and persistent activity, a potentially complex rotational profile, a statistically uncommon size, slight deviations in orbital solutions requiring further refinement. Individually, each of these characteristics can be contextualized within known cometary behavior. Collectively, they highlight how little is known about interstellar objects, and how wide the chemical and physical diversity of such bodies may be. As the object moves toward perihelion and then into the outer solar system, improved datasets, especially those gathered after solar conjunction, will help determine whether these anomalies reflect fundamental properties of Atlas or limitations in early observation. Regardless of the outcome, the scientific value lies not in whether the object ultimately proves typical or unusual, but in the insights gained through its study. Each observation advances the broader effort to understand how planetary systems form, evolve, and exchange material over cosmic timescales. In this sense, 3I Atlas is a reminder of the iterative nature of scientific discovery. Each inconsistency prompts a new question. Each question leads to new methods and observations, and each new dataset adds depth to our understanding of the universe. Rare interstellar visitors such as Atlas allow planetary science to extend beyond the boundaries of the solar system, without ever leaving it, offering glimpses into chemical environments shaped by different stars, different orbits, and different histories. The anomalies do not indicate mystery in the dramatic sense. They signal complexity, an opportunity to revise models, refine predictions, and appreciate the diversity of worlds that form across the galaxy. As observations of 3 Atlas accumulated during the months preceding its perihelion, researchers found themselves navigating a familiar pattern in the study of rare celestial objects, a mixture of results that aligned cleanly with established cometary models and others that resisted simple explanations. These irregularities soon came to be informally described as the object's 7 anomalies, not because they implied any fundamental violation of physics, but because each highlighted a gap in current data or understanding. When viewed through a scientific lens, these anomalies serve not as indications of extraordinary processes, but as prompts for deeper inquiry into the physical behaviour and chemical diversity of interstellar bodies. One of the earliest points of interest involved the object's brightness variability. Photometric measurements revealed fluctuations that did not settle into a stable repeating pattern, making it difficult to determine the rotation period. Rather than indicating unusual behaviour, this inconsistency is most likely the result of non-principal axis rotation, a tumbling motion observed in many comets, and the presence of surface regions with differing reflectivity or outgassing levels. Such complexities, while inconvenient for modelling, fall well within the expected behaviour of small, irregular bodies subjected to thermal and mechanical stress. Spectroscopic data introduced another layer of complexity. The high CO2 to H2O ratio observed in the outgassed material approximately 8:1 distinguishes 3I Atlas from most solar system comets, where water is typically the dominant volatile. Yet this characteristic is easily explained by formation scenarios outside the solar system. In protoplanetary disks, temperature gradients determine which volatiles freeze into solid grains. A body forming near the carbon dioxide frost line would naturally incorporate far more CO2 ice than water. Thus, what appears anomalous within the context of our solar system is entirely plausible in the broader diversity of planetary systems. Related to this chemical signature is the green-tinged coma detected by some telescopes. While striking in images, the coloration itself is scientifically conventional. Green emissions in cometary comae usually arise from excited diatomic carbon C2 or cyanide-related species under ultraviolet radiation. Their presence in 3I Atlas does not indicate unusual processes. Instead, it reinforces the notion that its nucleus contains a carbon-rich outer layer, shaped by long exposure to interstellar radiation. Early imaging also revealed subtle asymmetries in the coma, though the data lacked the resolution to determine a clear cause. Asymmetric comae are common, frequently resulting from localized jets, irregular nucleus shapes, or uneven solar heating. Without higher resolution observations such as those expected from Mars-based instruments, researchers cannot yet determine whether the asymmetry arises from physical structure or observational limitations. Another area of discussion involves the object's non-gravitational acceleration. Many comets experience slight variations in trajectory due to the reactive force of outgassing, and initial orbital solutions for 3I Atlas displayed small deviations from a purely gravitational path. These discrepancies initially appeared unusual, but became more consistent with expectations as additional observations tightened the orbital fit. Modelling such behaviour is inherently difficult without precise knowledge of nucleus geometry and rotation, and the early variations illustrate the limitations of working with incomplete data rather than pointing toward unconventional physics. A broader contextual point concerns the statistical rarity of an interstellar object of this apparent size. If 3I Atlas is indeed several kilometres across, it would be larger than both previously detected interstellar visitors. In the early days of interstellar object research, large bodies were assumed to be rare. However, the detection of only 3 objects does not support strong conclusions regarding population distribution. Improvements in wide-field surveys may reveal that large interstellar bodies are more common than initially believed, rendering Atlas less of an outlier and more of a representative example of undetected populations. Finally, researchers noted that the object's early thermal and activity profile did not perfectly match simplified solar heating models. Atlas became active sooner than expected, yet CO2 sublimates at far lower temperatures than water-making distant activity, entirely consistent with the CO2-rich surface. The early onset may reflect layers of exposed CO2 ice, or thermal alterations accumulated during its interstellar history. Once again, what appears anomalous underwater-driven models is expected within the framework of carbon dioxide-dominated chemistry. Taken collectively, these characteristics highlight the scientific value of 3I Atlas, rather than suggesting anything extraordinary. Each point draws attention to the limitations of current models, particularly those based on solar system comets. More importantly, they underscore how little is known about the chemical and physical diversity of interstellar small bodies, objects shaped by stellar environments fundamentally different from our own. Studying their deviations from familiar patterns helps refine broader theories of planetary system formation, disk chemistry, and the processes through which small bodies are ejected into interstellar space. The anomalies do not challenge the foundations of astrophysics. They simply reveal the complexity of nature at a scale that has only recently become observable. As new data arrive from Mars, orbiters' ground-based telescopes and post-perihelion monitoring many of these irregularities will likely find conventional explanations. Whether or not they do, the scientific value remains the same. Each observation contributes to a more complete understanding of how diverse, dynamic, and chemically rich the galaxy truly is. In this light, 3I Atlas stands not as an object of mystery, but as a meaningful scientific opportunity, a reminder that the universe routinely presents us with puzzles whose solutions deepen our knowledge rather than overturn it. Among the many challenges inherent in studying rare interstellar objects, perhaps the most persistent is not technical but cognitive. When astronomical events align in ways that feel significant, the human mind instinctively searches for patterns, connections, and hidden meaning. This tendency becomes especially pronounced when the available data are incomplete or ambiguous, as is the case with 3I Atlas, whose chemical signature, arrival timing, and proximity to Mars have sparked both scientific curiosity and widespread speculation. Yet a thorough scientific evaluation reveals that the most compelling mysteries often arise not from extraordinary phenomena, but from the natural intersection of limited data, observational constraints, and our innate drive to interpret the cosmos as a story. In the earliest weeks following its discovery, 3I Atlas became a focal point for online speculation, much of it amplified by the modern dynamics of digital information. Social media platforms by design reward emotionally charged and visually dramatic interpretations over careful analysis. When the comet's unusual carbon dioxide-rich spectrum and precise hyperbolic trajectory were announced, these details quickly became raw material for viral narratives about artificial origin, covert missions, or hidden significance. Yet in the discipline of astronomy, anomalous data points are not signs of intentional design. They are starting points for hypothesis formation grounded in physics, chemistry, and statistical reasoning. NASA's communications illustrate the proper scientific approach to such early anomalies. Rather than dismissing public concerns or speculating beyond the evidence mission, scientists clarified what had been observed and what had not. They emphasized that the available data, though unusual, were fully explainable through natural processes. A carbon-rich comet is unexpected, but not unprecedented. A hyperbolic orbit confirms interstellar origin, but implies nothing about artificial construction. A green coma can be striking in imagery, but arises from well-known molecular emission lines of diatomic carbon under ultraviolet radiation. In every instance, natural explanations remain not only plausible, but strongly supported by physical mechanisms. A key factor driving speculation is the inherent incompleteness of early data. Interstellar objects move rapidly, leaving astronomers with narrow windows for precise measurement. Initial orbital solutions carry uncertainties, spectroscopic measurements, struggle with low signal-to-noise ratios, and models must be continually refined as new data arrive. These limitations often produce temporary discrepancies, small shifts in trajectory, unexpected brightening, or uncertain compositional ratios that diminish as observations accumulate. Yet outside scientific circles, such uncertainties can be misinterpreted as intentional concealment or evidence of extraordinary behaviour. The case of non-gravitational acceleration provides a clear illustration. Slight trajectory deviations are expected for comets undergoing uneven outgassing, but early measurements can exaggerate or obscure these effects. In some public discussions, these deviations were compared to the well-known anomalous acceleration observed in 1I Oumuamua, even though the magnitude's contexts and physical explanations differ substantially. Where scientists see noise gradually converging toward a stable orbital fit, the pattern seeking mind sees hints of controlled motion. The contrast underscores the need to communicate not only results, but also the uncertainties and iterative processes inherent in scientific measurement. Another significant contributor to speculation is the object's coincidental timing. The arrival of an interstellar comet containing greenhouse-relevant volatiles at a moment when Mars exploration is revealing potential biosignature candidates can appear narratively significant. Yet coincidence alone does not constitute a pattern. The distribution of interstellar objects is not known well enough to define a baseline for expected arrival times, and scientific discovery on Mars progresses independently of distant celestial dynamics. Aligning these events into a causal narrative reflects cognitive bias rather than astrophysical insight. The scientific community must also contend with the legacy of earlier cycles of pseudo-scientific claims, such as myths surrounding Nibiru or periodic catastrophic visitors. Such narratives can prime the public to interpret any unusual astronomical event as part of a hidden cycle or conspiracy. While these claims lack any observational basis, they persist because they exploit deep-seated psychological mechanisms, particularly the desire for predictability in an unpredictable universe. By contrast, the behaviour of 3i Atlas aligns precisely with expectations for an object whose orbit is determined solely by gravitational mechanics and volatile-driven outgassing, not by intelligence or design. The scientific method provides tools to navigate these complexities. Source verification ensures that interpretations are grounded in peer-reviewed research rather than speculative commentary. Statistical literacy allows researchers to distinguish between genuine anomalies and selection effects arising from limited sample sizes. Predictive modelling offers a means to test hypotheses against future observations, reinforcing the principle that scientific claims must be falsifiable. Above all, the discipline requires tolerance for uncertainty, the recognition that incomplete data should not be inflated into definitive conclusions, whether ordinary or extraordinary. Crucially, none of this diminishes the genuine significance of 3i Atlas. Interstellar visitors remain among the rarest and most valuable objects available to contemporary astronomy. Their chemistry preserves information about the formation environments of other planetary systems. Their trajectories reveal the dynamical processes that eject small bodies into interstellar space. Their behaviour under solar heating expands our understanding of volatile retention and release under widely varying environmental conditions. These are profound scientific opportunities, made no less interesting by the absence of exotic explanations. What 3i Atlas reveals most clearly is a mismatch between the pace of scientific understanding and the speed at which digital narratives evolve. In astrophysics, conclusions develop gradually as data accumulate, models refine, and independent teams verify results. In online discourse, conclusions are often presented immediately and confidently, with little regard for uncertainty or methodological rigour. The challenge for researchers is to communicate clearly enough to prevent ambiguity from becoming fertile ground for misinformation, while still embracing the inherent uncertainties of early-stage investigation. Ultimately, the anomalies associated with 3i Atlas highlight not flaws in physical theory, but the limits of our current measurement capabilities and the adaptability of the human mind in interpreting the unknown. These characteristics are not obstacles to scientific progress, they're catalysts for it. Each irregularity invites deeper study, each uncertainty motivates improved instruments and observational strategies. By resisting the temptation to impose premature explanations on incomplete data, the scientific community preserves the integrity of inquiry and ensures that discoveries emerge from evidence rather than assumption. As 3i Atlas continues its journey through the inner solar system, it serves not as a harbinger of extraordinary events, but as a reminder of the delicate interplay between observation, interpretation, and imagination. The universe presents its mysteries without intent. It is our responsibility to meet them with clarity, discipline, and an unwavering commitment to understanding. The highly CO2-rich composition of 3i Atlas has prompted considerable scientific interest, not because it implies any form of artificial design, but because it challenges long-standing assumptions about how volatile ices are distributed in the protoplanetary disks of other stellar systems. The detection of a coma dominated by carbon dioxide with a measured CO2 to H2O ratio of approximately 8 to 1 places this interstellar visitor among the most carbon dioxide-rich small bodies ever observed. Understanding this composition requires a careful examination of cometary physics, comparative planetology, and the evolving theoretical framework of interstellar ice chemistry. Only then can we evaluate why this object behaves as it does, and why some interpretations such as the terraforming hypothesis have emerged in public discourse despite lacking empirical support. From a scientific standpoint, the presence of abundant CO2 is neither impossible nor unprecedented. In a protoplanetary disk, the positions of the ice line's boundaries where different molecules transition between gaseous and solid phases are determined by the thermal structure of the young system. If 3I Atlas formed in a region where temperatures remained cold enough for carbon dioxide to freeze, but too warm for water ice to condense efficiently, its nucleus could naturally accumulate far more CO2 than H2O. Such a formation environment implies a disk chemistry different from that of the early solar system, reinforcing the broader lesson that interstellar objects provide a unique window into planetary system diversity. Yet the interest surrounding 3I Atlas is heightened by a coincidence of timing rather than chemistry. Its arrival near Mars occurs during a period when missions like Perseverance and the Trace Gas Orbiter are uncovering increasingly compelling evidence for the red planet's ancient hydrological history and possible biosignatures. The juxtaposition of a CO2-rich interstellar object with rekindled scientific interest in Mars has motivated some commentators to ask whether the comet's composition might resemble the ingredients required for planetary atmospheric modification. Mars, after all, possesses a thin atmosphere composed primarily of carbon dioxide, and its long-term habitability has been shaped by the progressive loss of atmospheric volatiles to space. In this context, it is natural for the scientifically curious to wonder whether an influx of CO2-bearing material could have any measurable climatic effect. However, quantitative analysis quickly dispels the idea that 3I Atlas could influence Mars's atmosphere in any meaningful way. Even under generous assumptions regarding its size, density, and volatile content, its entire mass would contribute an insignificant amount of gas compared with the volume of the Martian atmosphere, let alone the quantities required for climate modification. Planetary atmospheres evolve over billions of years, shaped by volcanic outgassing, atmospheric escape, solar radiation, surface-atmosphere interactions, and magnetospheric dynamics. A single object, even a large interstellar comet, cannot substantially alter this trajectory. The terraforming hypothesis, while conceptually intriguing, does not survive basic atmospheric physics. What makes the hypothesis noteworthy from a scientific perspective is not its plausibility, but the underlying assumptions it reveals about how the public imagines interstellar travel engineering and planetary evolution. Human intuition often gravitates toward teleological explanations, interpretations that attribute purpose where there may be none. In the absence of complete data, meaning is projected onto coincidence. A comet rich in greenhouse gases approaches a planet whose atmosphere has thinned over geological timescales, and the mind searches for patterns, intentions, and narratives. This tendency, though psychologically understandable, must be separated from scientific inference. The scientific explanation for early outgassing from 3I Atlas lies in selective sublimation. CO2 sublimates at much lower temperatures than water ice, becoming active at greater heliocentric distances. If the nucleus contains a carbon dioxide-rich outer layer, solar heating will preferentially release CO2 until deeper water ice layers are exposed. The unusual ratio may therefore reflect not only formation conditions, but also stratified volatile layers accumulated over millions of years in interstellar space. Cosmic ray irradiation can further alter surface chemistry, producing carbon-rich crusts that mask deeper compositions. These processes are entirely natural and well modelled in studies of trans-Neptunian objects and long-period comets. The coincidence of the comet's CO2-rich chemistry with its proximity to Mars becomes less startling when placed in the context of observational selection effects. The interstellar objects humans detect are those that pass relatively close to the inner solar system and become sufficiently active for telescope detection. An object rich in CO2 will begin outgassing at greater distances and therefore be easier to discover than an object dominated by water ice that activates later. This introduces a bias into our sampling of interstellar visitors' bodies, with early onset volatile release are more likely to be detected and classified. The emergence of speculative frameworks such as engineered delivery systems illustrates a broader feature of modern science communication. When data are limited, narratives expand to fill the informational space. The scientific method demands that such narratives be evaluated based on their empirical testability. If an object were designed to release volatiles toward Mars, we would expect to observe directional outgassing anomalous acceleration inconsistent with sublimation or chemical gradients correlated with planetary proximity. To date, no such signatures have been detected. Observations remain consistent with naturally heated sublimation and conventional gravitational dynamics. Nonetheless, investigating such possibilities can be scientifically productive, not because they are likely to be correct, but because they clarify the constraints within which natural explanations operate. Asking whether a particular behaviour might indicate engineering forces us to refine models of natural activity, quantify uncertainties, and identify observational thresholds beyond which artificial signatures would become detectable. This process strengthens rather than weakens the scientific framework used to interpret rare phenomena. In the case of 3I Atlas, the scientific consensus remains firmly grounded in natural processes. The comet's chemistry reflects plausible formation pathways. Its activity aligns with CO2 sublimation physics. Its trajectory shows no deviation from gravitational expectations. The timing of its approach, though intriguing at a narrative level, has no known physical connection to Martian geological discoveries, and its potential contribution to Mars's atmospheric inventory is negligible by many orders of magnitude. Yet the object remains scientifically remarkable, not because it challenges physics, but because it enriches our understanding of how different planetary systems sculpt the small bodies they produce. Each interstellar visitor provides a data point in an emerging map of galactic chemistry, one that will become clearer as more such objects are discovered by future wide-field surveys. 3I Atlas serves as a reminder that the diversity of planetary systems is far greater than the local conditions of our solar system suggest, and that studying this diversity is crucial for building a comprehensive theory of planetary formation. Ultimately, the scientific value of 3I Atlas lies not in hypothetical terraforming scenarios, but in its ability to expand our observational horizon. Its CO2-rich composition helps illuminate the chemical processes that take place in distant protoplanetary disks. Its early activity highlights the importance of volatile stratification. Its interstellar origin underscores the dynamic interactions that populate the galaxy with wandering small bodies, and its passage through the inner solar system provides a rare opportunity to observe material forged around another star. Speculative interpretations may capture public imagination, but the true wonder lies in the natural processes revealed through systematic inquiry. In studying 3I Atlas, scientists are not uncovering evidence of engineered intent. They are uncovering evidence of a universe whose physical diversity exceeds our expectations and whose smallest fragments carry the signatures of worlds we may never see. The possibility of biological material associated with 3I Atlas has captured considerable public attention, largely because its arrival coincides with renewed examinations of potential biosignatures detected in Martian sediments. Yet the scientific assessment of such claims requires careful distinction between what is biologically plausible, what is physically possible, and what is simply evocative. Interstellar comets offer an opportunity to study the chemical ingredients that may contribute to the emergence of life, but their ability to carry or preserve biological organisms is constrained by well-established principles of radiation, physics, molecular stability, and astrobiology. The hypothesis that living organisms might survive an interstellar journey is highly speculative. The environment between stars is dominated by energetic cosmic rays, hard ultraviolet radiation, and particle fluxes that degrade organic molecules over timescales far shorter than the millions of years required for interstellar transit. Biological macromolecules are particularly vulnerable. DNA strands accumulate double-strand breaks, amino acids undergo radiolysis, and cellular structures cannot maintain integrity under prolonged exposure to vacuum and cryogenic temperatures. Laboratory simulations show that even extremophils known for extraordinary resilience cannot withstand unshielded interstellar conditions for geologically meaningful durations. Thus, the likelihood that 3I Atlas carries viable organisms approaches zero under current understanding. However, the question becomes more nuanced when considering chemical precursors to life rather than life itself. A comet rich in carbon dioxide, carbon monoxide, simple organic molecules and water ice represents a mobile repository of prebiotic chemistry. Many of the essential components for abiogenesis, carbon-bearing molecules, oxygen containing functional groups of volatile ices and reactive surfaces, can form naturally in molecular clouds and protoplanetary disks. These materials may survive interstellar journeys in modified but still informative forms. Their delivery to planetary surfaces has long been considered a potential mechanism for enhancing chemical diversity on young worlds. In this context, the arrival of 3I Atlas offers a valuable scientific opportunity. By studying its spectroscopic signatures, researchers can infer the types of molecules that formed in its natal system, providing clues to the chemistry that precedes biological complexity. Early data from JWST and ground-based infrared telescopes reveal carbon-rich volatiles but no evidence of complex organics such as amino acids or nucleobases. This absence is not surprising. Such molecules are difficult to detect remotely, unless present in unusually high concentrations. Instead, the observed chemistry aligns with simple precursors that could contribute to prebiotic pathways under the right environmental conditions. Public speculation has also gravitated toward the idea that 3I Atlas might activate dormant biology on Mars, a concept derived from popular interpretations of junk DNA activation and latent planetary ecosystems. Scientifically, this concept must be approached with caution. Mars today is a cold, arid world with a thin atmosphere, intense surface radiation, and limited sources of liquid water. Any biological activity would likely be restricted to subsurface niches, protected from ultraviolet radiation and oxidative soil chemistry. There is no evidence that atmospheric CO2 cometary volatiles or trace organic molecules could trigger biological reawakening. Biological systems require energy gradients, solvent availability, and suitable chemical environments, conditions not currently present on the Martian surface. Nevertheless, the psychological appeal of such narratives reveals how the public conceptualizes life in the universe. The idea that Mars may harbour dormant biology resonates with the broader question of how resilient life can be, how it persists or disappears, and whether planetary conditions can ever reverse long declines. Scientific investigation into the possibility of ancient Martian life remains a legitimate and active field of study, driven by rover-based sediment analysis, isotopic measurements, and mineralogical evidence of ancient aquatic environments. If life ever existed on Mars, its remnants, chemical or structural, might still reside in rocks awaiting sample return. The panspermia hypothesis offers another layer of scientific and philosophical reflection. Though frequently discussed in popular media, panspermia remains a minority perspective within astrobiology. While the transfer of prebiotic molecules between worlds is entirely plausible, the transfer of life itself faces significant challenges. Some models consider the possibility of protected microenvironments, such as subsurface pockets within large icy bodies that might shield biological material from radiation. However, no observational evidence suggests that 3I Atlas contains structures robust enough to preserve biology over interstellar distances. Even if such environments exist in some interstellar bodies, they would be exceedingly rare and difficult to detect. What makes panspermia scientifically valuable is not its likelihood, but its ability to broaden the conceptual framework through which scientists examine the origins of life. The hypothesis encourages examination of how organic molecules form in interstellar space, how they survive transport, and how they interact with planetary surfaces. In this sense, the arrival of 3I Atlas fits comfortably within ongoing research into the distribution of organic chemistry across the galaxy. Its study may strengthen models for how prebiotic materials accumulate on young worlds, even if it plays no direct role in Mars's biological past or future. From a methodological perspective, any claim of biological relevance must meet stringent evidentiary requirements. These include spectroscopic detection of complex organic molecules, isotopic ratios consistent with biological processes or structural signatures such as microfossils. None have been observed in 3I Atlas. Remote sensing instruments, including those on Mars orbiters, are capable of identifying some organic species, but cannot reliably detect structures or molecules associated with living systems. More definitive conclusions would require direct sampling, an endeavour not feasible for this object given its velocity and trajectory. Despite the scientific limitations, the arrival of 3I Atlas has stimulated renewed interest in astrobiology by highlighting the interconnectedness of planetary science, organic chemistry and stellar evolution. The object functions not as a biological agent but as an exemplar of the chemical diversity present beyond the solar system. Its presence encourages researchers to refine models of how organic and inorganic materials evolve in interstellar environments, how small bodies migrate between systems, and how these processes influence the potential habitability of planets. In the broader scope of astrobiological inquiry, the scientific significance of 3I Atlas lies not in speculative biological interpretations, but in the empirical evidence it may provide about the chemical architecture of planetary systems beyond our own. Understanding its composition contributes to a more complete picture of prebiotic chemistry in the galaxy, informs theories of planetary formation, and supports the search for environments where life might plausibly arise. The notion that 3I Atlas carries life seed's life, or awakens life, remains unsupported by data. Yet studying the pathways through which such ideas emerge, and the scientific constraints they must satisfy, offers valuable insight into both the possibilities and limitations of life in the cosmos. Interstellar objects remind us that organic chemistry is widespread, but that biology requires far more than ingredients. It requires environments, timescales, and conditions that align in ways we do not yet fully understand. As research progresses, 3I Atlas will be remembered not as a biological messenger, but as an interstellar chemical archive, a fragment of a distant system, offering clues to the universal processes that shape worlds and perhaps life itself. The scientific study of 3I Atlas has unfolded not only within observatories and data archives, but also within a parallel environment shaped by narrative psychology and digital information systems. While astronomers focus on photometric curves, spectroscopic ratios, and orbital solutions, the public discourse surrounding the comet reflects broader questions about how human societies interpret rare cosmic events. The trajectory of an interstellar object becomes intertwined with the trajectory of collective imagination. Understanding this interplay is essential for separating empirical conclusions from narrative constructs and for preserving the integrity of scientific inquiry in an era defined by rapid information flow and competing interpretive frameworks. Historically, comets have served as mirrors for cultural anxieties and aspirations. Before the development of astrophysics, these visitors from the sky were interpreted as omens, warnings, or symbols of transition. Although modern science has replaced superstition with quantitative understanding, the underlying psychological mechanisms remain. Unusual astronomical events continue to evoke interpretive responses shaped by narrative preference rather than physical evidence. In the case of 3I Atlas, the convergence of its interstellar origin, carbon dioxide-rich coma, and proximity to Mars has produced an interpretive environment unusually rich in speculation. Scientific explanations must therefore operate alongside and often in contrast to powerful cultural narratives. A central feature of this modern landscape is the influence of algorithm-driven information ecosystems. Platforms optimized for engagement tend to amplify interpretations that evoke emotion, urgency, or perceived secrecy. As a result, speculative explanations often spread more rapidly than measured scientific assessments. Claims suggesting hidden intent-engineered delivery or suppressed information flourish in such settings, not because they are supported by data, but because they are easily packaged, quickly consumed, and readily amplified. The scientific method, by contrast, progresses slowly through incremental data collection, peer review, and cautious interpretation. The tension between these timelines contributes significantly to the public understanding of 3I Atlas and similar phenomena. From an observational standpoint, the comet's passage highlights the limitations of remote sensing. astronomers possess extensive experience modelling cometary dynamics, but interstellar visitors present measurement challenges that exceed familiar boundaries. Objects like 3I Atlas travel at extreme velocities, undergo rapid changes in solar illumination, and exhibit volatile, rich outgassing patterns that evolve unpredictably as they approach perihelion. Early measurements often contain noise ambiguities and calibration uncertainties. As new observations accumulate, orbital parameters converge, chemical models refine, and earlier anomalies dissipate. Yet during this early window of uncertainty, speculation tends to fill the interpretative vacuum. Narratives form not because data indicate extraordinary mechanisms, but because the data are temporarily incomplete. The scientific value of interstellar objects lies precisely in this incompleteness. Each new observation forces researchers to re-evaluate assumptions about how different stellar environments shape small bodies. However, the gap between scientific uncertainty and public interpretation can be problematic. When chemical anomalies are reported before full contextual analysis, they may be perceived not as natural variation, but as evidence of intentional design. When a trajectory is refined over time, adjustments may be misinterpreted as concealment rather than routine model updating. These misinterpretations illustrate how cognitive biases influence the reception of scientific information. Patterns of belief are reinforced by narrative framing. A story suggesting that 3I Atlas could be part of a coordinated cosmic process appears more coherent and meaningful than the scientifically accurate alternative that the universe produces a vast diversity of small bodies, some of which occasionally pass near planets by chance. Humans are predisposed to prefer explanations that emphasize structure, agency, or purpose, even in systems governed entirely by physical law. This preference becomes especially pronounced when events involve celestial objects which historically occupied symbolic roles in human culture. Yet scientific discipline requires resisting the temptation to impose intentionality on natural phenomena. Rigorous analysis of 3I Atlas reveals no signatures of artificial origin. Its orbit matches the trajectories expected of unbound interstellar bodies. Its activity profile aligns with sublimation physics for CO2-dominated nuclei. Its compositional spectrum contains no molecular patterns indicative of engineered materials. The most scientifically productive interpretation remains the simplest. 3I Atlas is a naturally formed interstellar comet shaped by astrophysical processes in a remote planetary system and altered during its long passage through the interstellar medium. To evaluate claims of extraordinary behaviour, researchers rely on specific diagnostic criteria. Artificial propulsion, for instance, would manifest a sustained non-gravitational acceleration inconsistent with sublimation or solar radiation pressure. Complex structured radio emissions would suggest engineered communication systems. Thermal signatures departing from expected sublimation models might indicate internal heat sources. None of these signatures have been detected in association with 3I Atlas. In their absence, natural explanations remain overwhelmingly consistent with the available data. The broader challenge, however, extends beyond this single object. It concerns the development of a scientifically literate society capable of evaluating cosmic phenomena without being overwhelmed by narrative influence. This requires public understanding of the scientific process itself, particularly the role of uncertainty. Uncertainty in astrophysics is not evidence of concealment or extraordinary mechanisms, it is an inherent part of frontier science. As observations continue, uncertainty decreases, models refine, and conclusions strengthen. Recognizing this iterative process protects scientific discourse from distortions produced by premature theorizing. The case of 3I Atlas also underscores the importance of international transparency in astronomical research. Survey networks across multiple continents detect and monitor near-Earth and interstellar objects. Their data are publicly accessible, their methods openly documented, and their observations independently verified. This transparency makes large-scale concealment not only scientifically unnecessary, but practically impossible. When the scientific community states that no artificial signatures have been detected, that conclusion reflects the consensus of multiple independent systems, not the silence of a single institution. Still, the scientific fascination with 3I Atlas persists for legitimate reasons. Its unusual volatile composition expands the known diversity of interstellar bodies. Its early activation offers insights into thermal processing of CO2-rich nuclei. Its hyperbolic orbit reinforces dynamical models of small-body ejection from young planetary systems. Its close though safely distant approach to Mars offers an opportunity for comparative atmospheric chemistry via orbital instruments. These scientific opportunities stand independent of narrative elaboration. In the end, 3i Atlas illustrates a broader truth about the relationship between science and story. The universe does not shape its events to match human expectations. Patterns arise not from intention, but from the underlying statistical and physical processes that govern celestial mechanics. The task of science is to interpret these patterns without adding meaning that the data cannot support. The task of society is to cultivate the analytical resilience necessary to distinguish empirical evidence from narrative embellishment. 3. Atlas is extraordinary, not because it carries secret messages or engineered purpose, but because it provides a rare and valuable glimpse into the chemistry of worlds beyond our own. Its study reminds us that the universe is rich enough without requiring additional layers of invention. The scientific method remains our most reliable tool for understanding that richness, even as narratives compete to interpret it. As research continues in the months and years ahead, 3i Atlas will be remembered not for speculative stories, but for the empirical knowledge it contributes to planetary science, astrochemistry, and the evolving field of interstellar object research. Traveller, as we drift toward the end of tonight's quiet journeys, let us pause here, in the dim shadow of Mars, where an interstellar wanderer continues its silent arc. 3i Atlas came from a place we will never see, carrying chemistry older than our sun, older than every question we asked tonight. And still it moves without haste, without fear, without need for an audience. We have studied its orbit, its strange abundance of carbon ice, its brief alignment with a world that once held rivers and perhaps life. We have followed its path with telescopes and with imagination, and yet, observer, the truth remains wrapped in the thin dust between stars. The universe has not finished speaking. What 3i Atlas wants may be nothing more than what all objects of the cosmos want to continue, to endure, to pass through the light of a single star and return to the dark. And maybe that is enough. Tonight you and I stood at the edge of something vast, not to solve it, but to witness it. To remember that even the smallest moment of observation places us inside the same unfolding story as planets, comets, and ancient oceans on distant worlds. Let that be the lesson you carry into sleep, that wonder is not a conclusion, it is a rhythm. Rest well, traveller. The universe will keep watch. And if this story found you tonight, you may stay for the next.